Good morning again. So today is week 11. It's a new phase in our life in linear algebra. But before that, let's take a quick look at where we are in our linear algebra journey. We started way back when we were really young with the notion of linearity and how that led to the concept of vectors and matrices, and then some basic operations, the foundations, in the first couple of weeks. Then we moved on to the algebraic view, which was about solving Ax equal to b. So we did Gaussian elimination, Gauss-Jordan elimination, defined entities like ranks, inverses, and looked at the solvability of different shapes of matrices, etc. And then we graduated to the geometric view, which is like a superior view. So that involved vector spaces, bases of vector spaces, changes between bases, then the four fundamental subspaces given by a matrix, the column space, the row space, the null space, the left null space. After that, just last week, we investigated how to project any given vector to the column space of a matrix and how that makes things solvable. And then we reached an important milestone at that point, which is the application of that idea, the geometric view, in something that is really tangible in computer science, which is this very commonly used algorithm called linear regression, which is a predictive analytics tool, a supervised learning algorithm in machine learning. And that, at least for me, was a very satisfying moment because I could show you that all these abstract things that you were learning had some value in your real life. So that's where we stopped last week. And this week, we're going to move on to the advanced topics, the so-called advanced topics. But these topics are really not very advanced from the point of view of computer science, because these are the things that will be used almost every single data science kind of application algorithm. All these ideas that are coming up today and the next 2 weeks will be used. So eigenvalue decomposition is the first one, and that will lead to something else called singular value decomposition, the identification of components or directions in the data space that explains or contains the largest variance in the data, and using the linear combinations that will give you the largest variance in the data, you can start reducing the dimensionality of your data science problem. Dimensionality reduction is an important step in all kinds of data science applications, real projects. So that becomes something like almost like the first step that you would do in any kind of a data science project. All those things are coming up. They're advanced only in a sense that mathematically those things have to come only after all these things are done. But they're not advanced in terms of how they are actually used in computer science. Okay, so that's our learning journey. The objectives for today would be to understand eigenvalues and eigenvectors and to define them, to describe the significance of the concepts behind the eigenanalysis, and actually perform eigenanalysis for small matrices. And then from there, use eigenvalue decomposition, which is a way of writing a matrix in terms of its eigenvectors and eigenvalues. So that is a decomposition. And that is called, the process is called diagonalization. So the conditions for a matrix to be able to be diagonalized, that is the diagonalizability, and why that is used. Now let's take a step back and look at matrix as a transformation between spaces. That's the way we did when we were talking about Ax equal to b. So if you take a matrix A and then think of Ax equal to b, x is the input and b is the output. X belongs to Rn if the matrix is an m by n matrix, m rows and n columns. So it's a mapping between Rn, taking vectors in Rn and giving you vectors in Rm. It's a mapping from Rn to Rm. It's a transformation between two spaces. So that's the way we looked at it. Now if you take a square matrix, then the input space is Rn, the output space also is Rn. So in principle, if you think of it as an extension of the first statement, that these are actually two different Rns, but then since they are both Rns, we can think of it as the same Rn. So in other words, you can think of A as though it is taking a vector in Rn and transforming it in some way and giving you another vector in the same space. So let me give you some examples though to begin with. If you think of permutation, that is, it takes a vector and it shuffles the elements and gives it back to you. So that we saw, we had permutation matrices. Then we had the projection operator, which also takes a vector in Rn and gives you another vector in Rn, which is actually a member of a subspace, but it's still a vector in Rn. So if you take a three-dimensional vector in Rn and project it to the xy plane, I get a vector, and that vector that I get, the projection that I get, so it's got three components, even though the last component is actually 0. Then there's another class of matrices an operation that does what they call shearing. It returns a vector with one element changed proportional to another element. So we will see an example, then you will understand what I mean by that. So what it will do is to take something like a unit square and then give you a parallelogram that is actually a squashed version of the unit square. So that's why it's called shearing. Then rotation is another example that we saw. It also takes a vector and gives you another vector in the same space but at a different angle, pointing in a different direction without changing the magnitude or the norm of the vector. So these are the different examples. Any matrix that is a square matrix will be a mapping from one space to itself. And I think that mapping is called, if I remember right, automorphism. Now we can ask one question at this point. Are there some vectors that do not change the direction because of the transformation? In other words, I take a vector, all vectors go to some random vectors or some vectors defined by the matrix, but are there some special vectors that stay in the same direction but they just get scaled? So these vectors do not change direction. I put direction in quotation marks because in linear algebra, as it is applied in various fields, vectors may not be vectors with numbers, columns, or things in coordinate space where you can actually think of a direction. So that's the question that we are asking. So let's think about what no change in direction means. That means what you're getting is a scale version of the vector. In other words, suppose you take a vector S and you have a square matrix and you apply the square matrix to the vector S and you get a scale version. Let's call the scaling factor lambda. So you get AS, which is the application of the matrix on the vector S. What you're getting is lambda times S, where lambda is just a member of, it's a real number. It's a member of R. So are there vectors like that? And those vectors are called eigenvectors, and the corresponding value lambda is called the eigenvalue. So that's the definition. So let's look at a few examples before we proceed. Permutation. So if you have a matrix 0, 1, 1, 0, and if you apply it to a vector xy, x and y standing in a column, A, which is, and I want to take AX, this is going to be equal to YX. It just shuffles the elements. So it's a permutation matrix Y that the first element is a 0 times X plus 1 times Y, so that is Y. The second element is a 1 times X plus 0 times Y, that is X. Given that, can you think of a vector that will not change by the application of A? Obviously, if X and Y are the same, 1 and 1, then what you're getting is going to be the same because it changes 1, it shuffles X and Y, but they are both 1, so you get the same thing back. So that is an eigenvector of this matrix with the eigenvalue 1 because when you multiply, you get the same vector back. Now, if you have 1 and minus 1 on the other hand, when you shuffle these two, you will get minus 1 and 1 because X becomes Y and Y becomes X. So which is the same as minus 1 times the original vector. What I'm saying is if I take A times 1 minus 1, what I'll get is a minus 1, 1. But this is the same as minus 1 times 1 minus 1. So this is in the form AS is equal to lambda S. S is this vector or this vector, and lambda is minus 1. So two eigenvectors and two eigenvalues. Now if you take projection, if you project to the xy plane, so it's a 3 by 3 matrix, a square matrix still. The matrix, what that matrix does, if I multiply that matrix by x, y, z, it takes x of the first column, y of the second column, z of the third column, but the third column is already 0, so z becomes 0. So I'll get just xy, and any vector xy 0 will not change because it's already on the xy plane, and that will stay the same because I'm projecting onto the xy plane. So that will have an eigenvalue 1. So all vectors on the xy plane will be eigenvectors, the whole of xy plane. Now there is another eigenvector, that is I take any vector along the z-axis, that will become 0, it will become 0, 0, 0, and that is an eigenvector with the eigenvalue 0. So eigenvalues are allowed to be 0, but eigenvectors are not allowed to be 0. Eigenvalues can be 0. So in this case, the second eigenvalue is actually 0. Now, it looks as though we don't have eigenvectors corresponding to lambda equal to 1, but you can take any vector. So typically you would take the basis of the xy plane. The best basis would be 1, 0, 0 and 0, 1, 0, and that would be the eigenvectors corresponding to lambda equal to 1. So the whole xy plane is a space spanned by two eigenvectors, so we'll call that actually eigenspace. Now shear matrix, that is interesting. That takes a square and gives you a parallelogram. So an example is there, 1, 0, 5, 1. And let me show you what the matrix is. Well, what it does is fairly obvious. A10.51. So AX is a linear combination of the columns. The first one is 1, 0, that becomes x0, and I'm adding to that 0.5 times y and 1 times y. So the x component will become x plus 0.5 y, and the y component will become 0 plus y. So the y component stays put, and the x component changes in proportion to y component. So I have, in order to understand what any matrix does to the whole space, you would start with the columns of the identity matrix, the unit vectors, and we'll see what the matrix does to those vectors. So if I take Q1 and I say that doesn't change, but Q2 becomes 0.5 and 1, that is what the matrix does. The columns of the matrix were 1, 0 and 0.5, 1, but that's what it does. So Q1 prime, the transformed Q1, is the same as the original Q1, but Q2 became slanted. So if you think about the unit square there, what happens to that is that it becomes a slanted, sheared kind of a shape. It becomes a parallelogram. That is a shear matrix. That's why it's called a shear matrix. Let's just take 0, 1 and apply the matrix A to it. We know that it changes x in proportion to y, but y is 0 here, so x doesn't change. So x was 1, x is going to stay as 1, and y just stays put. So 1, 0 will stay as 1, 0. I have my A there. I'm going to take s, which was 1, 0. As is going to be, it is 1 times the first column and 0 times the second column, 1, 0. So lambda is equal to 1, and s, the eigenvector, is just 1, 0. But unfortunately, in this case, we could find only one eigenvector. For a 2 by 2 matrix, we would like to see 2 eigenvectors, but here there is only one, which is important. Keep that in mind. Just to remind you, rotation matrix is an orthogonal matrix, so that the transpose is the same as the inverse, and it's got trigonometric functions inside. Let me just show you why this is true. Again, in order to see what the matrix does, we will see what it does to the unit vectors. So Q1 is 1, 0 and Q2 is a 0, 1. Those are the columns of the identity matrix. If I'm rotating the unit vectors, the tip of the rotated version will be on that unit circle. If I rotate it by theta counterclockwise, my transformed vector corresponding to Q1 becomes cos theta sine theta by the fact that the norm of the red vector, norm of all vectors on the unit circle, is 1. And by basic trigonometry, you know that adjacent side is cosine and opposite side is sine, so you get that. Similarly, the blue vector rotating by theta will give you minus sine theta cos theta. So the rotation matrix is actually what it does to the first unit vector, cos theta sine theta, what it does to the second unit vector, minus sine theta cos theta. Now you can ask the question, for non-trivial, by non-trivial I mean if it is a 2 pi rotation, it comes back to the same position, so that doesn't change anything. But non-trivial, something like say pi by 2 or some random angle that is not an integer multiple of 2 pi, you will have a rotation matrix and all vectors in the plane are going to be rotated. Now, given that all vectors are going to be rotated, there are no vectors that will retain their original orientation or angle. So this matrix does not have any eigenvectors. So all vectors are changed. So there are no eigenvectors, but we will say that no real eigenvectors. We will see why later. The notion of eigenanalysis is not confined to vectors in the coordinate space where you have direction and angles. They are also applicable to vectors that are more abstract, like wave functions or functions. So one such example here for calculus differentiation, if you think of that as a linear operator or being applied on a vector which is just a function, this particular function, e to the power ax, if you differentiate it, a just comes out, and what you get, a is just e. So that function as a vector is an eigenvector of this differentiation operator with the eigenvalue which is a. Similarly, if you think of the second derivative of a trigonometric function like sine x, it is just minus sine x, so you get sine x back with an eigenvalue minus 1. So sine x is an eigenvector of a second derivative with an eigenvalue minus 1. So let me define this once more. For a matrix, a square matrix of size n by n, a vector in Rn is called an eigenvector with an eigenvalue lambda, which is a real value. Actually, I should relax this. For now, let's stay with real values. If I can write as is equal to lambda times s for a non-zero vector s, then s is an eigenvector and lambda is a corresponding eigenvalue. Now, one thing to note is that if s is an eigenvector, with a particular eigenvalue. Any scale version of S, so let's say R times S, is also an eigenvector with the same eigenvalue. If I take A times RS, R just comes out, that becomes R times AS, and AS we know is lambda S because S is an eigenvector. So it becomes lambda times RS. So if you think of RS as another vector, that also is an eigenvector of A with the same eigenvalue. That basically means eigenvectors define only directions. We're not really interested in the magnitude. So for that reason, we will typically just normalize the eigenvector. So if you do it in Sage Math, I believe you will always get the normalized version of the eigenvector. Now another thing is that lambda can be 0, as we saw in the projection matrix, projecting to the xy plane. And if it happens to be 0, what it's saying is that A times S is the 0 vector, which means S is a member of the null space of that matrix. So any matrix that has a null space will have a bunch of eigenvectors in the null space. But S is never a 0 vector, much like for the null space also we're looking for non-trivial vectors that are in the solution set. So here I'm relaxing the statement that for a real matrix in R n by n, the eigenvectors and eigenvalues may be complex. Let's take a look at how to compute eigenvalues, how to perform the eigenanalysis. So we'll start from the definition. So what we will do is take a matrix and we'll say that S is an eigenvector with eigenvalue lambda and S is not equal to 0, and we will just write A is equal to lambda S, and we'll try to take lambda S to the left hand side, and we want to pull out S eigenvector. You want to pull that out, and then what do you get? You get A minus lambda times I times S. Why do we get I there? Because you cannot take A minus lambda because A is a matrix and lambda is just a number. So in order to be able to subtract it, you have to actually multiply by the identity matrix, and then you get A minus lambda I times S is equal to 0. That is the requirement for eigenvectors and eigenvalues. So but what does that say? What it is saying is that some matrix A minus lambda I is some matrix times S equal to 0, where S is not a 0 vector. What's that saying? That's basically saying that that matrix that is multiplying S is a singular matrix, because a non-zero S multiplying that matrix is giving you 0. So the columns of the matrix are not linearly independent, they are linearly dependent. So it's a singular matrix. What do we know about singular matrices? We know that its determinant has to be 0. We know that the determinant of whatever is multiplying S here will have to be 0. So we can just write that, and now S has disappeared. There is no S there. The eigenvector is not there in this equation. And what is this equation? It's a determinant, and we know all the numbers in the matrix A, the square matrix, so we know all the numbers in I, it's just ones and along the diagonal. And lambda is the only unknown, n by n matrix. You can expand it along the top row, for instance, and it becomes a polynomial. So this determinant equation there, determinant equal to 0, is the same as a polynomial equal to 0. Is an equation that says a polynomial on lambda equal to 0. That polynomial, which is on lambda, is called the characteristic polynomial for the eigenvalues. If you can solve that polynomial, then you get all the eigenvalues. Theoretically, at least mathematically, that's how you do it. Practically, eigenvalues are computed using a completely different methods, but this is the mathematical way of doing it. A determinant equal to 0, determinant expands, and that gives you a polynomial equal to 0. A polynomial is on lambda, and just find the roots of the polynomial, and that's it. Those are the values, those are the eigenvalues. Okay, so we have to remember that this is the characteristic polynomial for the eigenvalues. By the way, the word eigen is a German word. It actually means characteristic in German. So, but nobody calls it characteristic vectors and values in English. We use eigenvalues and eigenvectors. But for the polynomial, you don't call it eigen polynomial. At least I don't think people usually call it eigen polynomial. We call it the characteristic polynomial. But if you hear eigen polynomial, somebody calling it eigen polynomial, probably because he's got German heritage or whatever, know that this is what they mean. Just stating that the determinant of A minus lambda I is equal to 0, that is the polynomial. No, that's a polynomial equal to 0, so that's the equation. The left hand side is the polynomial. Okay, so let's actually apply this and see how it works out for the examples that we did earlier. So we take the permutation matrix, A is there, and if I take A minus lambda I, what that means is that I subtract lambda from the diagonal elements. So I get lambda there, minus lambda there, minus lambda there, wherever I see 0 along the diagonal. And if I expand it, what do I get? It's the determinant is lambda square minus 1 equal to 0. That is the characteristic equation. Polynomial here and the equation there. And the roots of that would be lambda square equal to 1. So lambda is plus or minus 1. Those are the eigenvalues that we got for permutation matrix. And in order to get the eigenvectors, we take one of them. We take lambda equal to 1 and just put lambda equal to 1 in a minus lambda I. So you get, wherever you see lambda there, you get 1. So minus 1 and 1 and 1. And you want this a minus lambda I times s equal to 0. How do you get 0 out of this? What kind of linear combination of the columns will give you 0? Just add them. So the vector that is multiplying this to get the 0 vector would be just 1 and 1. So take the first one and take the second one, add them, and that linear combination will give you 0. So the eigenvector corresponding to lambda 1 is equal to 1 is just 1, 1. Similarly, if you take lambda equal to minus 1, wherever you see lambda, you put minus 1. So you get 1, 1 and 1, 1. Matrix is singular. If you do Gaussian elimination, you just subtract the first row from the second, you get 0, 0. All those things. The second row is pivotless. But can you tell me why this guy is singular? Is it singular to begin with? And if so, why? It has to be singular because we found lambdas such that the matrix is singular. So when you take a minus lambda I for the solutions of the characteristic equation, you have to have singular matrices. Good. So here we get 2 eigenvectors in R2, which is pretty good, and we have R2 matrices 2 by 2 matrix, and we are looking for 2 eigenvectors and 2 eigenvalues. Very nice. Now we can see that these 2 eigenvectors S1 and S2 are actually orthogonal to each other. If you just take S1 transpose S2, you get 1 times 1 minus 1 times 1, so it's 0, so the dot product is 0, so they're orthogonal. That is not an accident. It is because all real symmetric matrices have full set of orthogonal eigenvectors. Full set means if it is an n by n matrix, I have n eigenvectors and they're orthogonal too. Real symmetric matrices are the good members of the family of matrices. They're not quite the kings, but they are close to being the king. They're like maybe like the prince. Now let's take the projection matrix. So that is the projection matrix. By the way, is the projection matrix real and symmetric? So it is real and symmetric. It's obvious. It's right there. It's a diagonal matrix. And if I subtract lambda I from it, I would be subtracting lambda from the diagonal elements. So I get 1 minus lambda, and minus lambda. And if I take the determinant, that would be just the product of the diagonal elements because everything else is 0. So I get that lambda times 1 minus lambda square equal to 0. Now I get lambda, the solutions would be lambda equal to 0 or lambda equal to 1 or lambda equal to 1. So lambda equal to 1 comes with a multiplicity of 2. And that multiplicity, because it is coming from the characteristic polynomial, is called the algebraic multiplicity. So lambda equal to 1 has an algebraic multiplicity of 2. Lambda equal to 0 has an algebraic multiplicity of 1 because it's only 1. It's not lambda square equal to 0, it's lambda equal to 0. With that, we can easily find the eigenvector because you just put lambda equal to 0, you get 1, 1, 0. And what multiplies 1, 1, 0? To give you 0 vector. So you have to multiply the first one by 0, the second one by 0, and the third one you can multiply by anything because that is already 0. So 0, 0, 1 multiplying this guy will give me a 0 vector. So that would be an eigenvector. Now about the other eigenvalue lambda equal to 1, if I do that, I can multiply the first column by anything, second column by anything, and the third column has to be multiplied by 0 because there's a 1 there, and then I'll get a 0 vector. That means my second eigenvector is some number and some other number x and y and 0 in the z position. Now it is not just a vector, but it is actually a whole plane of vectors. It's a large number of vectors. Anything in the xy plane really is an eigenvector. So we can actually choose the vectors out of this space, subspace that is the space of eigenvectors. Obviously it's called the eigenspace for lambda equal to 1. So you can choose any 2 orthogonal basis vectors out of them. So the most obvious one to choose would be the x vector and the y vector, the unit vectors along x-axis and y-axis. If I do that, then those are orthogonal to each other. So I have to kind of modify my statement that said for a real symmetric matrix, you have a full set of orthogonal eigenvectors. What I mean is that you can choose vectors if you have an eigenspace, and choose vectors such that you have a full set of orthogonal eigenvectors. Now, the dimensionality of the eigenspace is called the geometric multiplicity because it's about the space. The good thing here is that the algebraic multiplicity is 2. The geometric multiplicity corresponding to the same eigenvalue is also 2. So 2 and 2, that is a good case. Now, the shear and rotation matrices, let's take a look at those. The shear matrix was that, and if I do A minus lambda I to get the characteristic polynomial and equation, what I get is in the diagonal I get 1 minus lambda, and 1 minus lambda whole square is equal to 0, because 1 minus lambda times 1 minus lambda minus 0 times 0.5, that is a determinant. So I get lambda equal to 1 and 1, similar to the projection matrix that we looked at, with the algebraic multiplicity of 2. So that doesn't bother us much. Now if you put lambda equal to 1, you get that matrix, because wherever you see lambda you put 1, so 1 minus 1. And you can see that in order to get a 0 out of this matrix, you just have to take any multiple of the first column and the 0 multiple of the second column. So that is an eigenvector. But you cannot find another eigenvector. There's only one eigenvector here. There's no other eigenvector. But the geometric multiplicity is actually 1. So that is a bad situation. Saying that the geometric multiplicity is 1 is the same as saying that there's only one eigenvector. Shear matrix is a kind of matrix that does not have full set of eigenvectors, and that's it. So algebraic multiplicity is not geometric multiplicity. This situation is a bad situation. Now if you look at rotation, this is rotation for pi by 2 is skew-symmetric, it's anti-symmetric, which means A transpose is minus A. And if you do the characteristic polynomial, which is the determinant of A minus lambda I, you get lambda square plus 1. So lambda times lambda minus lambda times minus lambda, that is lambda square, minus 1 times minus 1, that is lambda square plus 1 equal to 0. So you get lambda is equal to plus or minus I. So we're stepping in the scary field of complex numbers here. And if you actually plot along and actually plug in the value I and try to compute the eigenvectors, then you get the first eigenvector to be 1 minus I, the second eigenvector to be 1 I, etc. So you get complex vectors also. So the vectors are in C2, not R2. So it is like the opposite of the symmetric case. In symmetric case, we had real eigenvalues, and real skew-symmetric matrices will have purely imaginary eigenvalues. Alright, let's move on to the properties of eigenvalues and eigenvectors. So these properties are quite interesting. The first one says that the sum of eigenvalues is actually the trace of the matrix. Trace, if you remember, is just the sum of the diagonal elements of a matrix. And the statement is that the sum of the eigenvalues is actually the trace of the matrix. The proof is interesting. So if you think about the characteristic polynomial, well, assume that you have the eigenvalues lambda I, then the roots of the characteristic polynomial will have to be the same as the eigenvalues. So what I'm saying is that the roots of the characteristic polynomial will have to be lambda I, because lambda I are the eigenvalues. So characteristic polynomial is a polynomial on lambda. So if I have lambda minus lambda 1 times lambda minus lambda 2 times all the way up to lambda minus lambda n equal to 0, and if I were to expand the factors there, lambda minus lambda 1, etc., I would get a polynomial of the order n. What are the roots of this particular polynomial? It will be lambda I, lambda 1, lambda 2, etc. Because for any one of them, at least one of the factors will be 0, the whole polynomial will be 0. So those are the roots. So this is one way of implementing the roots. Now what's the coefficient of lambda to the power n here? If I expand this out, that's actually very easy. How do you get lambda to the power n? You'll get 1 lambda from here, 1 lambda from here, and so on, and the nth lambda from here. All of them will come with coefficient 1. So what's the coefficient of lambda to the power n? It is just 1. But I also wrote the characteristic polynomial as a minus lambda I, the determinant. So if I think about it, I have terms like a1 minus lambda, a22 minus lambda, and so on in the matrix, ann minus lambda, and I have some other terms all over the place. So this is my huge matrix, and it's the determinant of that matrix that I'm looking at. If I expand it, the lambdas will come only from the diagonal, so that's the only place where you have lambdas. And if I expand that, there will be a term, because if I am expanding it along the first row, the minor is actually the determinant of this guy here, and then that determinant will have another minor that is here. So all the minors will have the leading element, which is aii minus lambda. If I multiply it out, there will be one term that basically reads a11 minus lambda, a12 minus lambda, all the way up to ann minus lambda, plus some other things after that. Okay, there will be other things after that. But from this, can you see the coefficient of lambda to the power n will be? It is plus or minus 1. To be more precise, it's going to be minus 1 to the power n, depending on how many n's you have. So if I want to say this is the left-hand side and that is my right-hand side, I want to equate them, then I have to make sure that the coefficient of lambda to the power n is the same. So I can write a minus lambda I is equal to minus 1 to the power n and the product of all those terms there, and that will be in the shorthand notation a pi I equal to 1 to n, that is a product of lambda minus lambda I. So I can always write it that way. Now we talked about the coefficient of lambda to the power n. What's the coefficient of lambda to the power n minus 1? Lambda to the power n minus 1 in the expansion of the blue polynomial, blue factorized polynomial in the top, plus 5 times lambda plus 6. What's the coefficient of lambda here? So the expansion is quadratic, so there will be terms in lambda square, lambda and constant. What's the coefficient of lambda here? 11, because this is basically 5 plus 6. Well, let me take one more, lambda plus 1. In that case, what's the coefficient of lambda squared here? It's going to be 12 in this case. So similarly, the coefficient of lambda to the power n minus 1 in this case is going to be the sum of lambda i's, sum of eigenvalues. And what's the coefficient of lambda to the power n minus 1 in the red area here, the red polynomial that I have written down here? That is going to be the sum of a11, a22, a33, ann. It will be basically the sum of the matrix elements, because that's where lambda to the power n minus 1 will come. Coefficients of left hand side and right hand side, lambda to the power n will have a coefficient of minus 1 to the power n. Lambda to the power n minus 1 on the left hand side will have the trace, which is the sum of all the diagonal elements of the matrix, because a11 plus a22 plus a33, etc. On the right hand side, it will be the sum of the eigenvalues. So they have to be the same, because this equality is a statement of truth, and that means each coefficient will have to match. Alright, so that is the statement. So the proof is right here, just by comparing the coefficient of lambda to the power n minus 1 on the left hand side, you get the trace. On the right hand side, you will get the sum of the eigenvalues. Now that proof or that statement has a corollary that states that for a real matrix A, the trace is always real because all elements are real. That means if you have complex eigenvalues, they have to appear in complex conjugate pairs so that the imaginary part will cancel off. That is one property, quite important and quite interesting. The second property is actually interesting also, but easier to prove. The product of the eigenvalues that I've written down here, and that is the determinant of the matrix. And again, that goes back to the same statement here. A, the characteristic polynomial on the left hand side is a minus lambda I, the determinant. On the right hand side, I'm just expanding it in terms of the roots. And this is again a statement of truth, should hold for all values of lambda because it's an equation. And in particular, I can put lambda equal to 0. And on the left hand side, I'll get determinant of A. On the right hand side, minus 1 to the power n and a product of n entities minus lambda I. So there's minus 1 to the power n coming up again. So that will cancel off to 1. So that is just a product of the eigenvalues. But this also has a corollary which states that if you have a singular matrix, we know that the determinant has to be 0. That means at least one of the eigenvalues will have to be 0. So the eigenvalues will tell you something about the structure of the matrix, the arithmetic structure of the matrix, the trace, the determinant, the singularity, etc. Quite interesting. Another set of properties, eigenvalues of real symmetric matrices are real, and the proof is there in the textbook. So what we are saying is that it's a real matrix, square, transpose is the same as itself, so it's symmetric, and that implies that the eigenvalues are all real. The opposite, the converse of this also is true. The eigenvalues of real skew-symmetric matrices are purely imaginary, which is what we saw for the rotation matrix. So if A transpose is minus A, then lambda I will be such that its complex conjugate is minus the number. So remember, the complex conjugate for A plus bi, the complex conjugate will be just changing the sign of I, is A minus bi. And if the complex conjugate is a minus of the original number, that means it's purely imaginary. the imaginary part changes sign. There's one more set of properties. If you scale a matrix by alpha, the eigenvalues will scale by the same factor alpha. So if A has eigenvalues lambda I, the eigenvalues of alpha times A would be alpha times lambda I. This is fairly easy to prove. So what we have is AS equal to lambda S, because lambda is an eigenvalue. And if I just multiply both sides by alpha, I get alpha times AS is equal to alpha times lambda times S. And then you can see that this matrix, call it B or A prime, has an eigenvector S with the eigenvalue alpha times lambda. Next one also is easy to prove. If you shift a matrix by alpha, I'll tell you what shifting means. The eigenvalues will get shifted by alpha. If you take A and add alpha times I to it, that is what we mean by shifting the matrix. Shift the diagonal elements by alpha. Then the eigenvalues of that shifted matrix will be lambda I plus alpha, where lambda I are the eigenvalues of the original matrix A. Again, easy to prove. So we have AS equal to lambda I times S for some eigenvector corresponding to lambda I. Now I just add alpha I to A and multiply by S. So I expand it out. I get AS plus alpha IS. So that is lambda IS because AS is lambda IS. And then I have alpha S because I multiplying S will give me just S. And then I can pull out S. I'll get this guy. Again, if you call the matrix A plus alpha I A prime, some other matrix, then that multiplying the same eigenvector will give me some constant times the same eigenvector. But the eigenvalues will get shifted by alpha. So these are things that might be important in developing algorithms for computing eigenvalues and eigenvectors. Now let me tell you the properties of eigenvectors. This is an interesting property. Eigenvectors corresponding to distinct eigenvalues are linearly independent. That means if you have a matrix, a square matrix A, and you have some eigenvectors, and if I have two eigenvalues lambda sub I and lambda sub j, then if lambda I sub I is not equal to lambda sub j, that means Si and Sj are going to be linearly independent. That means you won't be able to find a linear combination such that the linear combination is 0 without the coefficient being 0. This is proven in the textbook again. Now the thing is, it actually applies not merely to real matrices, it actually applies to the complex matrices too, because the proof actually involves complex fields. Another thing that we mentioned earlier, real symmetric matrices have full set of orthogonal eigenvectors, and that means if A transpose is equal to A for a real symmetric matrix, then the eigenvectors are orthogonal to each other. Again, proven in the textbook. The eigenvectors of a shifted matrix A plus alpha I are the same as those of A. So we proved this. A plus alpha I times S is going to be equal to lambda plus alpha times S. So eigenvalues get shifted by the same factor, alpha, but the eigenvectors are the same. Now, the last one, that is actually about eigenvalues. I put it as the last one because this one I don't have a proof for. So for a real symmetric matrix again, the number of positive eigenvalues is the same as the number of positive pivots. So if you do Gaussian elimination without any scaling, you scale, of course, you can change the sign of the pivots. Without any scaling, if you just do Gaussian elimination, then the number of positive pivots will be the same as number of positive eigenvalues. The number of negative pivots will be the number of negative eigenvalues. Combine that with the fact that you can shift the eigenvalues, then what you can do is to take a matrix, find the number of positive and negative pivots, and then shift it by a little bit, and then see the number of positive pivots and negative pivots again. And that way you can zero in on the eigenvalues, because the moment the number changes, then you know that you have crossed the value of one eigenvalue in terms of alpha. And that can be used as the basis of an algorithm to compute the eigenvalues. This is not a very good algorithm. This is not the way it is implemented. There are better algorithms now. So this property, connecting the sign of the pivots to the sign of the eigenvalues, is called Sylvester's law of inertia. This got something to do with mechanical engineering or physics or something. One thing that is important for you to know is why we're doing this eigenanalysis. So in order to show you that, let's talk about what a matrix does to a vector or all vectors. So let's take a matrix that is given here, 5 by 4 minus root 3 by 4 minus root 3 by 4, 3 by 4. As we know by now, what that matrix does to the unit vectors q1 and q2, 1, 0 and 0, 1 will be the columns of A. The first column will be what q1 will become. 0, 1 when transformed will become the second column of the matrix A. So now we know what it does to these two vectors, but it looks quite complicated. So if I take other vectors, other unit vectors in the unit circle, suppose I have a unit circle there, so I'm taking other vectors on the unit circle so that the magnitude is the same and transforming each one of them, what will happen is that you will get a bunch of vectors, transformed vectors, whose tips are on the ellipse as shown here. But to understand the ellipse, it's not very easy. So you have some direction somewhere, A1 in light red and A2 in light blue, and then you have an ellipse, but nothing is specified about the ellipse. But if you do the eigenanalysis, it will find for you the axis of the ellipse. So the first eigenvector that comes out of this eigenanalysis is actually along the axis of this ellipse, and the second eigenvector is along the other axis of the ellipse, and the length of the axis will be the eigenvalue. So in this case, the dark red eigenvector, it is normalized, so it's on the unit circle that points in the direction of the major axis of this ellipse, and the size of the major axis is just the eigenvalue lambda 1. The blue eigenvector and the corresponding eigenvalue will be lambda 2 and s2. So that's what it is doing. So it's basically specifying the ellipse to which a unit circle gets transformed by the matrix. That is actually enough to specify everything that is happening because of the matrix. So basically, eigenanalysis will specify and help you understand what a matrix does. So if you have the columns of the matrix AI, and if you have the identity matrix where the columns are QI, those are the unit vectors, what the matrix does to the unit vectors in the identity matrix is what it's going to do to every other vector. So it maps the unit vectors to its columns. So A is a mapping of the unit vectors QI to AI. So it will take the unit circle, by which I mean every vector pointing to any point on the unit circle, will become a point on the ellipse. So it will transform those vectors to vectors whose tips are on the ellipse. Okay, so that's what it's going to do in R2. But if you go to Rn, then instead of a unit circle, you have a unit hypersphere. There is a hyperellipsoid. So that is a transformation. So that is an extrapolation to higher dimensions. Now, we need to know what the ellipsoid is in terms of its orientation, which would be the eigenvectors, and we need to know the size of the ellipsoid. Those would be the eigenvalues. So eigenvectors will give us the principal axes. Even at this point, you can ask the question, why do we want to know the principal axis and the size of the ellipsoid, etc. So let me give you a concrete example here. So in data science, if you have a data set, which is a matrix, if you consider data, let's take the concrete example of the height, weight, and length of hair. Suppose I take the average in each column, which is like just adding up and dividing by the number of observations. So I get one row of averages. Now suppose I subtract it from each row. So I take the average in each column, the mean of each column, and subtract it out from each entry. And now suppose I plot it again. Suppose I take one column of say height, and I plot after taking out the mean. What do you think the mean of that plot will be? If I have weight, that is one column, then I have height and length of hair. I have some numbers here, W1, W2, up to Wn, and I take its mean, so that would be W sum divided by n. And then I go back and subtract it out of each one of the W's. New W prime, W1 prime is equal to W1 minus this, let me call that W, minus the mean. And now, suppose I make a plot, or suppose I compute the mean of W prime. So the mean, I add up all the W1 prime, W2 prime, etc. and divide by n. What do you think that mean will be? That's going to be 0 because I basically took out the mean. That process is called zero centering the data. So I can do that for each column here. So I zero center the data. Now suppose this data matrix, I call that A after zero centering. And now I take A transpose A. This will be a 3 by 3 matrix. This is the gram matrix, by the way. That is going to be the covariance matrix of the data. Or you can actually do this, just write down the equation and compare it to the covariance equation in statistics, and you will see that it's actually the covariance matrix. Each entry in that 3 by 3 matrix will be the covariance between the corresponding variables. So the diagonal elements will be the variance and the off diagonal elements will be the covariance. Suppose I run the eigenanalysis on the covariance matrix, then I'll get an ellipsoid. The direction along which you have the largest eigenvalue is the largest, and that particular direction captures the largest amount of the variance in the data. That particular linear combination of the features will capture the largest amount of the variance in the data. So instead of working with weight, height, and length of hair, I might work with a linear combination specified by the eigenvector, and that will give me the largest covariance. So I might be able to get away by using just one variable in my model, because that might give me, let's say, 80% of the variance, and suppose I'm happy with 80% of the variance being explained by my model. If that is enough, then that will be a good strategy for reducing the dimensionality of the problem. In fact, if you have, say, 150 different features, and if you want to reduce the dimensionality to, say, 10, this is exactly what you will do. You will compute the covariance matrix and will run an eigenvalue analysis on it, and will take the top 15 or 10 or 15 of the eigenvalues, and then take the corresponding directions as the directions along which you have the largest variance, and that might be enough. That might capture 99% of the variance in the data, and your model might explain a large part of it. This is a good strategy, and this is actually what is being done in singular value decomposition and the associated principal component analysis. But as you can see, the amount of variance that you can potentially describe by your model, that is related to the coefficient of determination coming from statistics. Remember, coefficient of determination R square is actually the fraction of the variance that is explained by your model. This is the basis of dimensionality reduction, and there is one more application, not necessarily for data science projects, but for mathematical modeling in other applications. So that is diagonalization. So right in the beginning I said eigenvalue decomposition will help you write the matrix A as a product of three matrices, in which the middle one is actually diagonal. So suppose I want to write A as some matrix S, and some matrix which is completely diagonal, so lambda, and S inverse. So I'm reusing the letters S and lambda, so it's got something to do with the eigenvectors and eigenvalues. So if you can write it in this form, this is actually a very good situation to be in any kind of a chain or difference equation kind of modeling of a system. So if you describe the system as a vector, and you say that at every step, at every iteration, the system changes by a matrix multiplication, it changes into something else. So at step 0 you have x0, at step 1 you have x1. I have some system, and it is fully described by a vector x0 which has got a large number of components, measurements of the system maybe, and that is at time t0, time instant or time sequence number t0. And in order to get x1, that is going to be ax0. Suppose that is x1. So evolution of the system is modeled by a matrix multiplication A, and which depends only on the previous state. And if I want to get x2, then that will be ax1, that will be x2, which is the same as a square x0. So you have to square the matrix. This kind of modeling, by the way, in which the state of the system depends only on the previous state, nothing beyond that, the memory is only one step, that is called a Markov chain kind of modeling. There's another model called hidden Markov model, which is also based on this kind of idea, and that is used in text analytics, in parts of speech, tagging of words, etc. So what I'm trying to say here is, if you keep going, suppose you want to know xk, that is basically going to be equal to a to the power k x0. So you may need to take powers of the matrix. Now, if you can write the matrix in this decomposed form, taking a square will mean multiplying this twice, and in between what you have is S inverse S, which becomes I, so that disappears, and then you have lambda square. Lambda square is a lot easier to compute compared to a square, because lambda is a diagonal matrix, and the square, you just take the diagonal elements and square it. So a to the power k will be just two matrix multiplications and an exponentiation of the diagonal elements of one matrix, so which is a lot easier to do than multiplying a k times. Without diagonalization, if A is an n by n matrix, the best algorithm we have to do the multiplication, the complexity is of the order n to the power 2.3. And if I have to do it k times, then it's k times n to the power 2.3 operations. That is what you will need. With diagonalization, it takes only two matrix multiplications, so that costs me 2 times 2 n to the power 2.3. And then I have not k but n exponentiation, because I have n elements in the diagonal of lambda. I have to raise each one of them to the power k. Let me call that n operations. Then that total is n plus 2 times n to the power 2.3. And if you compute the saving, you will see that it is actually k by 2. If I want to take, say, 100 power of it, I save a factor of 50 in that operation if I had diagonalization. So if I would take, say, 50 minutes to compute the multiplication, it will take only 1 minute to compute the same thing using diagonalization, plus maybe a little bit of time to actually do the diagonalization, but that's negligible. So that is a kind of a thing that you can get by diagonalization, in specifically from the perspective of computer science, savings in terms of computational complexity. So why take powers? It's a common technique in difference equations and Markov chains that I just described. In fact, we can define exponentiation of matrices through Taylor series expansion, and that is actually used in solving differential equations, but that's not part of this course. So difference equation that I showed you just now basically says that the kth state depends only on the k minus 1 state through a matrix multiplication, and if I expand it, xk actually depends on the original state x0 by a to the power k, which we can actually use our diagonalization to compute very easily with the saving of k by 2 operations, a factor of k by 2. So it's a common method to model mathematically using difference equation, and which are computed iteratively. So that much for the motivation. What we do is we start with the eigenvalue equation. A times Si is equal to lambda I times Si. So Si is an eigenvector of A with the eigenvalue lambda I. So that is the statement there. And suppose I arrange all these eigenvalues in a matrix S as columns. Then I go ahead and arrange all the eigenvalues as the diagonal elements in another matrix, a square matrix, n by n matrix, like that. If I do that, then suppose I compute A times S. So A times S will be A times the matrix S, which has columns S1, S2, S3 standing there. And as you know from the block multiplication from the first chapter, that is basically distributing A inside and applying it to each one of the columns. So I'll get AS1, AS2, A up to ASN. But Si is an eigenvector of A with the eigenvalue lambda sub I. So I'll get lambda 1 S1, lambda 2 S2, lambda I Si, lambda n Sn, like that. So that is one side. Let me call that the LHS. Now if I look at the other side, suppose I take S times lambda. So S is just the vector S1, S2, S3 up to Sn, and I have lambda, which is a diagonal matrix. If I do the multiplication, what will happen is something like I have S1, I'll just take 2 eigenvectors, that is my S matrix, and my lambda is a lambda 1 and lambda 2 and 0 here, 0 here. In order to get the first column of the product, I'll take lambda 1 times the first column and 0 times the second column. So that product will become lambda 1 S1, and the second one, similarly, I'll take the 0 times the first column and lambda 2 times the second column. I'll get lambda 2 S2. The product S lambda, if I extrapolate that to n vectors standing side by side, is the same as a matrix with lambda 1 S1, lambda 2 S2 up to lambda n Sn standing side by side. So that's what I wrote there. So S lambda is lambda 1 S1, lambda 2 S2. If I compare that with AS, which also is the same thing, so this guy is the same as that, then you can see that they are the same. So I can say confidently that AS equal to S lambda. So AS equal to S lambda. That is always true, regardless of how many eigenvectors you have, what algebraic multiplicity is, and geometric multiplicity. All those things are irrelevant, because whatever we did not make any assumption. AS equal to S lambda is always true, which means if I multiply both sides by A again, what will happen on this side? AS is equal to S lambda. I put S lambda there, and I multiply by A again, and I get A square. And then on the other side, lambda just gets squared. So A to the power k S is equal to S times lambda to the power k. That also is always true. Now, if I make an assumption that S is invertible, what that means is that we have n linearly independent eigenvectors. If that is the case, then I can take S to the other side. I can multiply both sides with S inverse. AS is equal to S lambda, always true. But if S is invertible, I can multiply both sides with S inverse, or AS S inverse is equal to S lambda S inverse. and this guy becomes I, and that just goes away. So A is equal to S lambda S inverse, and which was the decomposition that we're looking for. So that decomposition is possible if S is invertible. So if you can find the linearly independent eigenvectors, then you can write that. But if you can find linearly independent eigenvectors, then you can use that as a basis also. So there is a nice basis called the eigenbasis. So any vector in Rn, because I have n linearly independent eigenvectors, can be expressed as a linear combination of the eigenvectors. So if I call that linear combination with scalars Ci, then I can see that x0 is actually just the matrix S times C, which is a vector. So that vector C would be the vector x0 expressed in the eigenbasis. Why would you want to do that? Because the difference equation xk, which is the kth state of the system, was a to the power k times x0, and if x0 is actually sc, then a to the power ks, as you can see here, is just s lambda to the power k. So it just becomes that, which is easy to compute. This guy is hard to compute, but this guy is very easy to compute. So the diagonalization is a process of getting A in this form, and this, since it is a decomposition, a factorization, this is also called eigenvalue decomposition, or EVD for short. That is a pretty interesting and very useful decomposition. Now let's look at one fun application of eigenanalysis. So it's the Fibonacci series, the Fibonacci sequence of numbers. It happens in nature all the time in terms of the spirals and spirals going in opposite directions or stuff like that on pineapples and sunflowers and all that. Okay, so that is the Fibonacci sequence, and it's got very interesting properties. Interesting sequence is very easy to compute. K plus 2 element is the sum of the previous two, k plus 1, and the kth elements. Sum them up. It is, if you think about it, it's like a Markov chain. Instead of depending only on the previous step, it depends on two steps. So it's a second order difference equation if you want to be very formal about giving it the right name. Now the question that you might ask ourselves is, how fast are these numbers growing? These numbers are obviously growing. It's 1, 1, 2, 3, 5, 8. And it doesn't look like there is any clear way in which you can compute how fast these numbers are growing. And even more impressive, can you come up with an approximation for the kth Fibonacci number? That also doesn't look at all obvious here. But eigenvalue decomposition, the eigenanalysis, will tell you that it is actually possible. Of course, in order to do anything to do with eigenvalues and eigenvectors, obviously you need to have a matrix, and we don't have any here yet. So we will create first order matrix equation. So a second order difference equation will become a first order matrix equation. Let me consider a vector which has two elements, a Fibonacci number and the previous Fibonacci number, k plus 1 and k. And if I do that, then if I want to compute the next vector, that is x sub k plus 1, so wherever I see k, I'm going to put k plus 1, so k plus 1 plus 1 and k plus 1 here. So I get that. Now I get fk plus 2 as the first element, but I know that fk plus 2 is fk plus 1 plus fk. So I put that in there, then suddenly I can see a matrix there. I can see that the k plus 1 state, that vector, is actually the kth vector times a matrix. Now that is my matrix A. It's 1, 1, 1, 0. And then I can go ahead and do the eigenanalysis. I write the characteristic equation, A minus lambda I, the determinant of, and I get that, and expand out the determinant 1 minus lambda times minus lambda minus 1, and do a bit of basic algebra. Then I get lambda square minus lambda minus 1 equal to 0. That quadratic equation is just about the most famous quadratic equation in the world, the most significant one. But before telling you why that is the case, let's compare that equation, lambda square, lambda and 1, coming with minus signs there, and compare it to our second order equation there, and take everything to one side. So fk plus 2 minus fk plus 1 minus fk. So k plus 2, that is second order, k plus 1, that is first order, k, that is the 0th order, and the right sign and right coefficients. So that is actually, the characteristic equation actually captures the essence of the Fibonacci sequence. From the properties of eigenvalues that we talked about, some of the eigenvalues of the matrix A will be the same as the trace, which is, what is the trace here? 1. And the product will be the same as the determinant. What's the determinant here? minus 1. But we have the characteristic equation, and this is a quadratic equation. We know how to solve it. So I just solve it. You will get lambda is equal to 1 plus or minus square root of 5 divided by 2. That number again is actually a very famous one, especially the positive one. So lambda 1 is 1.618, and that is actually the golden ratio. 1 plus square root of 5 divided by 2. Golden ratio, again something that appears in all kinds of aesthetic kind of stuff like paintings, architecture. Has got very important properties in terms of how we perceive things apparently. But as you will see, it is also significant in terms of Fibonacci numbers. So there is a connection between Fibonacci numbers and this golden ratio, which is interesting. So lambda 1 is actually the golden ratio. Now, the absolute value of lambda 1 is more than 1. The absolute value of lambda 2 is less than 1. So the statement I'm going to make is that the sequence is going to grow as lambda 1, because that is what we call the dominant eigenvalue, because that is the highest in terms of absolute value, and it is more than 1. So the system is actually going to grow exponentially, and the growth rate is going to be 1.618. So that means if I take the 100th Fibonacci number divided by the 99th Fibonacci number, that ratio is going to be very close to lambda 1. That is my statement. In order to see why, we will have to look at the vector that we constructed, which had, remember, fk plus 1 and fk. We can express that in the eigenvector basis with some coefficients. We don't really need to know the eigenvectors yet. We just need to know that it can be expressed. I have two eigenvectors. They are orthogonal to each other, and I can express any vector. In particular, I can express x0, which was just 0, 1, I believe, or 1, 0 rather, in terms of the eigenvectors. And then I know that xk is going to be a to the power k times that x0, which means it's going to be c1 times a to the power k s1, c2 times a to the power k s2. And since s1 and s2 are eigenvectors, I know that a to the power k s1 is the same as lambda 1 to the power k s1, and the second one is lambda 2 to the power k s2. So this we already saw. Now look at lambda 1. That absolute value is more than 1. Lambda 2 absolute value is less than 1. So as k grows, as k becomes like 10 or 15 or 100, this guy is going to just disappear, because lambda 2 to the power k is going to be a very small number. But lambda 1 to the power k, on the other hand, is going to be a large number. So we can ignore this guy, and we can say, regardless of what s1 is and regardless of what that coefficient is, we know that xk is going to grow in accordance with the dominant eigenvalue. So xk is kind of similar to that which grows as the dominant eigenvalue. If you want to actually know what exactly that Fibonacci number is as an approximation, the Fibonacci numbers are going to grow as the golden ratio, which means the 100th Fibonacci number divided by the 99th Fibonacci number is actually going to be the golden ratio, 1.618 whatever. But if you want to actually be able to compute the 100th Fibonacci number as an approximation, then we need to find the eigenvalues and eigenvectors. Eigenvalues we already have, but we need to know the eigenvectors, and we need to express x0, our starting vector, the starting state vector, in terms of the eigenvectors, in the basis of eigenvectors, in the eigenbasis. We can actually see that the eigenvectors s1 is lambda 1, 1, and s2 is lambda 2, 1. That is easy to see. Okay, so this is what I want to do. If I take s is equal to lambda and 1, what do I get? I get lambda minus lambda square plus 1 in the top, and in the bottom I get lambda and minus lambda. And the second element is obviously 0. The first element is actually the characteristic equation. Remember, our characteristic equation was lambda square minus lambda minus 1 equal to 0. Multiply by minus 1, you get the top one, so that also is equal to 0. Eigenvectors are of the form this, so I have lambda 1, 1 as 1 eigenvector, I call that s1, and lambda 2, 1 as a second eigenvector, I call that s2. We know that the approximation for xk is whatever linear combination we have for x0, and we ignore the second term there, s2 is ignored because that is going to be multiplied by lambda 2 to the power k, and so we need to worry only about s1. And if I do all the multiplication out and expand it, I'll get fk plus 1 is equal to c1 lambda 1 to the power k plus 1, fk is equal to c1 lambda 1 to the power k, and obviously fk plus 1 divided by fk is of course lambda 1, which is the golden ratio. But as you can see, fk is just c1 lambda 1 to the power k. So we need to find C1 also. And then we have an approximation for Fk. C1 lambda 1 to the power k. So what is C1? In order to get C1, we look at x0, and that is 1, 0. So the first Fibonacci number is 1. The 0th one is 0 in our sequence. And we express that as a linear combination of the eigenvectors. So I have that. And that basically gives me two equations. C1 lambda 1 plus C2 lambda 2 is equal to 1. That is the first one. And C1 plus C2 is equal to 0. That is the second one. Two equations, and we know we are experts in solving equations of that kind. And so I'll get C1 is equal to 1 divided by square root of 5. So Fk, the kth Fibonacci number, is 1 by square root of 5 coming from C1, and lambda 1 was the golden ratio to the power k. So I have an expression there for the kth Fibonacci number, a numeric expression, which depends only on k. And this is actually surprisingly extremely accurate. By the time you reach the fifth Fibonacci number or something like that, you will see that the error in the approximation is a few parts in a million. It is very, very accurate. So that is the application of eigenanalysis in something that was a series of numbers, a very famous series of numbers, but a series nonetheless. Of course, this is only an academic exercise, but similar applications can be seen in other kinds of difference equations and how systems evolve. And you will see that the approximation is actually a very good one. Let me wrap it up very quickly. So we looked at the eigenanalysis and the significance, definitions and significance. Vectors that scale when transformed rather than change orientation, those would be the eigenvectors. And it gives insights about what the matrix does, especially in the data space. That would be principal component analysis, which can be used for dimensionality reduction. So there are many, many ways in which eigenanalysis is used in physics and engineering. And we looked at eigenanalysis for small matrices, example matrices, and we looked at characteristic polynomial and then some properties, and diagonalizability and the uses of diagonalization. We looked at it, and then an example, an academic example in Fibonacci numbers. So one thing about systems where you have eigenvalues for the system would be to predict whether the system is stable. Is it growing, or is it shrinking, or is it oscillating between states? Those things will be described by the sign and the size of the eigenvalues. Sylvester's rule, a starting point for some eigenvalue analysis. A transpose A, we saw many times that the Gram matrix is a very good matrix.